Hi everyone, I am Behnaz Ranjbar, a PhD student at the Chair of Processor Design at Houston. Today I'll be presenting my paper Improving the Timing Behavior of Mixed-Criticality Systems using Chebyshev's theorem. First off, what is a mixed-criticality system? In these systems, tasks with multiple criticality levels are integrated onto a common hardware platform. Criticality is a designation of the level of assurance against failure, and the platform can be single or multi-core processors. Many industrial applications, such as avionics, automotive, and medical devices, are evolving into mixed criticality systems. In general, since there are different tasks with multiple criticality levels running on a common platform, different operational modes exist in these systems. We have to guarantee the complete and correct execution of tasks with higher criticality levels in any mode to prevent catastrophic damages. Low criticality tasks are executed in these systems as well, and normally all these tasks have to be executed correctly before their deadlines. If the system switches to the emergency mode, some tasks with lower criticality levels can be dropped to guarantee the correct execution of HC tasks. However, depending on the application, we may not be allowed to drop many LC tasks and degrade the quality of service. For MC tasks, multiple worst-case execution times are defined corresponding to the multiple criticality levels. So if you consider two criticality levels of tasks in the system first starts its operation in the low mode, and all tasks are scheduled with the low WCET. If the execution time of at least one HC task exceeds its low WCET and the output is not ready, then the system switches to the high mode. And in this mode, to guarantee the correct execution of HC tasks, some or LC tasks will be dropped, and the high WCETs are considered for scheduling HC tasks. As can be seen, two WCETs are defined for MC tasks. The high WCET is pessimistic, and many works have been presented to determine the pessimistic WCET of a task by analyzing its control flow graph. It's a conservative execution time bound, and in general, there is a high gap between the average case execution time and high WCET. But what about the low WCET? How can we obtain it? What is its role in designing the MC systems? This figure shows the time distributions of samples of a task. As shown, most samples' execution time is significantly lower than the high WCET. Now, if there is a high gap between the low WCET and high WCET, more tasks, especially LC tasks, are scheduled at design time. However, it may cause frequent system mode switches, and consequently there are more LC tasks in the high mode at runtime. If this gap is small, it reduces processor utilization due to the scheduling of fewer tasks at design time. Therefore, low WCET plays an important part in providing a reasonable trade-off between the number of LC tasks scheduled at design time and the probability of mode switching at runtime to improve the quality of service. Most previous work set the low WCETs as a percentage of the high WCETs, and this percentage may be different for each task. We executed 20,000 instances of quicksort algorithm with different input sizes. This table shows how many instances violate the low WCET if it's set to different values. We see that the high WCET is not an appropriate parameter to determine the low WCET. For example, by setting the low WCET to 1/16 of high WCET, there are different rates of exceeding it. So it is not feasible to determine a general formula to find the low WCET based on the high WCET, while setting based on the ACT seems more practical. Besides, by increasing the application's input size, the ACT and the high WCET growth are not the same, so the ACT cannot be counted as a percentage of the high WCET. As a result, we introduce a new scheme that provides a general formula to choose a suitable low WCET based on the ACT to make a reasonable trade-off between the mode switching and the system utilization. So we introduce a new theorem based on the Chebyshev's theorem. In Chebyshev's theorem, if x is a non-negative random variable and we have the mean and variance of x, then the following inequality is satisfied for any positive real number of a. Now, by using this theorem, we introduce a new theorem, in which if we set the low WCET based on the ACT and variance, for any positive value of n, the rate of exceeding it is bounded with 1 plus n squared. As I explained, there is a trade-off between the system utilization and mode switching. So there are two main objectives to optimize the system. We improve the utilization by allocating a significant gain in terms of utilization to LC tasks in the low mode. Both objectives are computed based on the value of n, which is introduced in the previous slide. So this equation must be optimized and solved to find the optimum value of n for tasks. The proof and the optimization problem has been explained in detail in the paper. To evaluate the proposed scheme, first we analyze the mode switching probability. In this experiment, we executed 5 applications with 20,000 different inputs in the mid tool. This table shows the percentage of overruns for both our analysis and experiments. It shows that the mode switching probability for each task in the experiments is much less than the analysis for any value of n. We expect this result because the analysis provides an upper bound which is valid for any task with any execution time distributions. Since this upper bound is very pessimistic, as future work we need to find a tighter bound of mode switching probability. Now we investigate the effect of varying parameter n on maximum utilization and mode switching probability. We also show the optimization goal here, which is based on the system utilization and mode switching. These results are for a random task set that the utilization of HC tasks in the system is 85%. The first figure shows that by increasing n, which means having a higher low W set, both maximum utilization assigned to LC tasks and the probability of mode switching are decreased. While to achieve the best optimization, we need to maximize utilization and minimize mode switching probability. Here we show the result for n equals to 5 and 20. As can be seen, the mode switching has a higher decreasing rate than the utilization. The second figure shows the optimization goal, in which the optimum n is 18 for this task set. In this slide, we compare the objectives under our proposed scheme and the other policies. As mentioned previously, the current policies, like these 3 papers, use the different percentages of high W set to obtain the low W set. Since all articles have the same policy, we choose one of them as a representative methodology of all works. In our approach, by increasing the utilization of HC tasks, the maximum utilization assigned to LC tasks is decreased, and the mode switching probability is increased. Now, if we focus on different lambda values, considering a large lower bound value reduces the probability of mode switching, but it underutilizes the system during runtime. On the other hand, using a smaller lower bound value for lambda, increasing the maximum utilization, but with the high mode switching probability. The last figure shows that by optimizing both system properties, the proposed scheme performs better than other policies. As a result, our scheme improves the utilization by up to 85.29% compared to the existing approaches, while mode switching is bounded by 9.11% in the worst case. In the end, we evaluate 2 different mixed criticality scheduling algorithms in terms of acceptance ratio under our proposed scheme. We generated 1,000 random test sets and reported the average results for each utilization point. In the method of paper 4, all LC tasks are dropped in the high mode, while in 7, the algorithm executes all LC tasks in the high mode by reducing their W set to 50%. As can be seen, for both papers, the acceptance ratio is improved significantly. The reason for having a better acceptance ratio under our proposed scheme is determining the appropriate low W set for HC tasks and executing more tasks in the system. To conclude our presentation, we propose an offline scheme to determine the low W sets for mixed criticality tasks based on the Chebyshev's theorem. We showed that the mode switching probability, system utilization, and schedulability are optimized well by using our proposed scheme compared to the other policies. As future work, first we would present a better solution to find a tighter bound for mode switching probability. Then we would extend our scheme for systems with more than 2 criticality levels. In addition, we would evaluate the approach with real benchmarks on hardware platform to show its efficiency. Thanks for your attention.